Welcome to This Explainer. Today, we are unpacking the sheer engineering genius behind a totally game-changing piece of space tech. We are talking about the Nancy Grace Roman Space Telescope's Coronagraph Instrument, which is basically the ultimate technology pathfinder for future space-based planet hunting. So picture this fundamental physics problem. When we look up at the night sky, we easily see stars. But capturing light directly from an exoplanet orbiting one of those stars, that is an entirely different beast. The planet's faint reflection is completely overwhelmed by the intense glare of its host star, which can be literally a billion times brighter. So how do we bypass that blinding glare? Here's our roadmap for today to understand how we conquer this. We will cover the exoplanet imaging problem, the Coronagraph instrument itself, what it means to dig the dark hole, the actual observing scenario, the community participation program, and finally, how this paves the way forward. Let's jump right in. Section 1. The exoplanet imaging problem. Let's start with the massive physical barrier standing between us and seeing these hidden worlds. You know, taking pictures of exoplanets isn't just about having the biggest zoom lens. You could literally have the largest telescope in the universe, and you still wouldn't see the planet if you can't block that intense host star glare. I mean, it is the ultimate contrast problem. We have to somehow suppress that overwhelming, saturating light so the incredibly faint planetary reflection can finally pop out of the shadows. Section 2. The Coronagraph Instrument. This brings us to our technological solution, a demonstration that will fundamentally change how we hunt for planets. This is where it gets incredibly cool. The coronagraph actually treats light as a physical substance. It uses a complex system of specialized pupil masks and prisms, but the real magic is that it creates an opposite wave. Basically, it generates a light wave that has peaks where the starlight has valleys and valleys where the starlight has peaks. When these waves interact, they completely cancel each other out. Pair that with large format deformable mirrors to fix tiny optical flaws, plus ultra-sensitive electron multiplying cameras, and you have a recipe for absolutely unprecedented clarity. And here is the actual hardware making this possible. You've got those large format deformable mirrors I just mentioned, the highly specialized pupil masks, and those ultra low noise photon counting cameras. By combining all these pieces together in the vacuum of space, engineers are pushing the boundaries of high contrast imaging way past anything we could ever pull off from the ground. Section 3. Digging the dark hole. To actually get these tools working together, engineers have to pull off a highly precise maneuver. Now, just to be clear, when we say dark hole, we are definitely not talking about a black hole in space. Instead, think of it as a meticulously cleared, deeply dark zone right around the host star. It is the sweet spot where our instrument's opposite waves have successfully canceled out the starlight, giving us a pristine viewing area where wavefront control is fully effective. That is the exact zone where we can finally spot what's lurking in the orbit. But to actually dig this hole and maintain stability, the instrument first has to calibrate using a reference star, and this star has to meet some seriously strict criteria. First off, it absolutely must be a single star to avoid any stray photon noise contamination. It also has to be exceptionally bright, with a visual magnitude of less than 3, which basically acts like a giant flashlight to speed up the digging process. On top of that, it needs a tiny angular diameter, so it essentially looks like an infinitely small pinpoint of light. And crucially, it has to be located super close to our actual science target, so we don't ruin the telescope's thermal stability when shifting views. Section 4. The observing scenario. Once we are fully calibrated, we get into the incredibly complex sequence of actually taking the observations. You have to realize directly imaging an exoplanet isn't just a quick point-and-shoot snapshot. It is a grueling, active, multi-hour endurance test. The observatory spends over 10 hours alternating back and forth. It acquires wavefront sensing probes on that bright reference star, calculates the necessary corrections down on the ground, touches up the wavefront, and then finally observes the target star where the planet actually lives. And separating a true planet from annoying camera glitches, which we call speckles, requires two absolutely brilliant tricks. Step 1 is Angular Differential Imaging, or ADI. This is where the whole observatory literally rolls up to 15 degrees. Because the stars rotate but the instrumental speckles stay put, we can untangle what's real from what is just a glitch. Step 2 is Reference Differential Imaging, or RDI. This involves taking that pristine reference star image and mathematically subtracting its leftover speckle pattern from our target star image. Because we constantly need to bounce back to the reference star for calibration and wavefront touch-ups, Actual observing time is incredibly precious. In a given 24-hour observing period, the instrument will realistically only achieve about 14 hours of actual integration time on the science target. The entire rest of the clock is dedicated simply to making sure our dark hole remains perfectly dug. Section 5, the Community Participation Program. Because, as you might guess, none of this automated precision happens without a massive human effort behind the scenes. This is where the Community Participation Program, or CPP, comes in. It is this incredible international group bringing together experts from the US, the European Space Agency, JAXA in Japan, and other global partners. They are the ones actively designing the execution phase of this entire technology demonstration. The meticulous groundwork laid by the CPP is literally what feeds the autonomous space robot. They are tasked with preparing the data reduction software and, critically, maintaining the essential target databases. They're the ones out there scouring the sky for the absolute best science targets and painstakingly vetting those ultra-bright reference stars we just talked about. Their main goal is to verify all the baseline tech requirements while making sure we extract the absolute maximum long-term science value for the whole astronomy community. Section 6, paving the way forward, because ultimately the Roman chronograph is a massive stepping stone. By proving that active wavefront control, deformable mirrors, and ultra-low noise detectors can survive and perform flawlessly in the harsh environment of space, this instrument is quite literally writing the playbook for the next generation. It is directly validating the exact technologies that will one day serve as the heart of the upcoming Habitable Worlds Observatory, a mission concept completely designed to hunt for life. Which leaves us with a pretty mind-blowing thought. Once we completely master the art of canceling out the stars, and once we perfect the engineering of digging the dark hole, just how crowded with habitable worlds might our universe truly be? Thanks for joining me on this explainer, and keep looking up.